This is Rick Karg of Residential Energy Dynamics, and this is the Energy Out West session, Building Science Tools. What you're looking at now is the Residential Energy Dynamics REDCalc free page. You're not seeing the whole thing, just part of it. And what I'm going to do is go over some building science tools as fashioned into free web applications by Residential Energy Dynamics, sometimes known as RED. I'll walk you through 4 of over 25 building science tools. These include ASHRAE's 62.2 2016. Here's a slide out menu. Here's 62.2 2016. Air leakage metrics, a very useful tool. Depressurization analysis, and finally DensePack insulation. If I scroll down here, you'll see that the free tool is right here for you to fill in and get your answers. I'll go through the detail of each of these 4 building science tools for you, and if you wish, you may get in touch with me by email. This is Rick Karg of Residential Energy Dynamics. I'm going to walk you through the use of the REDCalc free ASHRAE 62.2 2016 ventilation tool. This short video is a good place to start if you want to quickly learn about the use of this calculation aid. Please watch the extended version video tutorial if you want to learn more about the details of this useful web application. This REDCalc free tool is for sizing dwelling unit ventilation in new and existing dwellings in both single-family and multifamily buildings. I'm going to start from the top of the tool and work down. First of all, the top section of the tool. The ASHRAE's 62.2 standard treats new and existing construction differently. You can see you have a choice here, new or existing. Parts of the tool will disappear when you choose one or the other. The example that I do will be for existing buildings. The next item is dwelling unit is detached or attached to other dwelling units. This is new to the 2016 version of the ASHRAE standard. If you want to know more about this, please watch the extended video tutorial. The next and final input for this section of the tool is use infiltration credit. You have a choice of yes or no. We recommend that you choose yes for most cases. For one case, when you would choose no, would be a multifamily building that has dwelling units in it that are stacked, that is, one above the other. The ASHRAE standard does not allow any infiltration credit for that. So in that case of stacked multifamily dwellings in a multifamily building, you would choose no. Otherwise, we recommend that you use yes. The next section of the RED tool is closest to weather station. Select either the United States or Canada. I've selected the United States. You can select one of the 50 states. I've selected Colorado. And here you see for a particular state, you will see the cities that are listed for weather stations. I have chosen the Denver International Airport. After choosing those 3 drop-downs, we get the result of the weather and shielding factor of 0.59 for the Denver International Airport. I want to look now at the building data section right here, starting with floor area, where I have entered 2050. Continuing with the building data section, and I have scrolled the tool a bit. Next, number of occupants. You have choices here in a drop-down of from 1 to 10 occupants, as you can see. The next input in the building data section of the tool is building height. The standard assumes 2.5 meters as the height for one floor. If you convert that to feet, that is 8.2 feet. I have put 17 feet in this example. The last input in this section is the measured leakage at 50 pascals. I have entered 1400 CFM at 50 pascals, or CFM 50. This is a measurement you get from a blower door for the whole house. This is an important value. It is needed for the infiltration credit, just as the building height is needed for the infiltration credit. Next, I'm going to talk about the alternative compliance path of the ASHRAE 62.2 standard. For the details of the alternative compliance section of the red tool, first of all, you can select or deselect the kitchen. And notice I have entered values here already. If I deselect the kitchen, you can see it goes away. If I select it, the number I've already entered is there, 65. And then for bathrooms, I can select anywhere from 0 to 5. If I select 5, notice what happens. I'm going to go back to 2 for my example, 2 bathrooms. Then in this part of the table, I have the fan flow. Now, the ASHRAE standard states that the fan flow must be measured. The existing fan flow must be measured. So that's what we have here. Does it have an openable window or not? If it has an openable window, that has an impact on the total deficit over here. Kitchen 65, I measured it, has an openable window. I check that. It makes no difference whether it has one openable window or 7. I click this and I get a credit toward the deficit of 20. Bath number 1, I measure it. It has a fan flow of 25 CFM. Bath number 1 has an openable window. It has a total deficit of 5 CFM. Bath number 2, I measure the fan. It has a CFM of 30. No openable window because it's on the interior of the house. Therefore, it has a deficit of 20. And the entire deficit, all of these added together, adds up to 40 CFM. Now for the dwelling unit ventilation results. By the way, before the 2016 version of the 62.2 standard, this was called whole building ventilation. First of all, effective annual average infiltration rate. This is a value that you get from your blower door test, and it's an averaged constant flow rate that has the equivalent effect on air quality as the real year-round ventilation infiltration rate. So that's the infiltration. Next, an important number is the total required ventilation rate, or Q-tote. Now, Q-tote comes from the equations that are now listed on the slide as an overlay. Q-tote is the total amount of ventilation that we need. This will be made up of natural air leakage and mechanical ventilation. Next is the alternative compliance supplement. That comes from the alternative compliance path section of the tool just above. And remember, for our example, the total deficit was 40. We divide that by 4, and that gives us 10. So that number gets added to the 91 from Q-tote. So now we have 101. Next is the infiltration credit. This comes from our blower door test also, and it is Q-inf for infiltration. So we have 91. We add the alternative compliance supplement to that. We subtract the infiltration credit amount. This is the amount that is coming from natural air leakage, and the remaining amount is the required mechanical ventilation rate, or Q-fan. For this example, that is 44 CFM. Let's take a quick walk together through the air leakage metrics tool. This is both a REDCalc Free tool and a REDCalc Pro tool. We call this a solve all tool because you can solve for all of these results at the bottom by just entering one input in the bottom section of the tool and 2 or 3 in the top section. You click the radio button for the metric that you wish to enter, and it gives you corresponding leakage values for all of the other ones. Quite an amazing tool. Usually there's no reason to enter the surface area at the top of the tool. I'm going to take that out right now, click outside of the box, and you see that the only corresponding metric that goes away is leakage at 50 pascals divided by the surface area. I'm going to put that back now so I don't forget about it. Click outside the box like that. So up top in the top section of the tool, you would enter floor area, volume, and surface area only if you are interested in leakage at 50 pascals per surface area. And as with all of the REDCalc Free and Pro tools, if you click on a label either for an input, black font, or a result, blue font, it will give you what we call pop-up help. You engage it like this and then get rid of it by clicking again. Let's now look at a little more detail at the inputs in the top section of the tool. For the floor area, we have 2,500 feet. We're assuming this is a 2-story house. The volume is that amount times 16 feet of height. I've used math on the fly here. Remember, it's a 2-story house. Each floor is 1,025 square feet, so I have multiplied that times 2. So we have 2 times 1,025, and then we have that quantity times 8. This is math on the fly. If I click outside of the box now, it will give me the result. Then for the surface area, which you only need, remember, for this metric down here, if you are interested in it, this is what Passive House uses for their air leakage metric. If we come back up here to surface area, I've used math on the fly here. What I've got is the one side of the house. The house is 40 feet by 25.5 feet. And then we also have to include the floor, and we have to include the ceiling. So we have the floor of 1,025. We have the ceiling of 1,025. We have the sides of the house, 40 plus 40 plus 25.5 plus 25.5. And each of those sides is 16 feet tall. So if I click outside of the box, what I get is 4,146 for the surface area. I recommend to you that you leave the pressure exponent at the default value of 0.65. Let's look at a few of the air leakage metric values, and I also want to let you know which my favorite one is. Remember that all of the answers down below, except for the entered one, the leakage at 50, which is CFM 50, all of those are based upon the items that we put up here at the top, which are primarily the dimensions of the building we're looking at, except for the pressure exponent, which characterizes the leakage of the house. As I've already said, it's a good idea to leave that alone. The one I think we're all most familiar with down here is the leakage at 50 pascals. That's the same thing as CFM 50 leakage. So I've said that's 1400 CFM50. Now, some of you might have heard of, gee, if you take the CFM50 and divide it by 10, it gives you the approximate leakage area in the envelope. What that actually is the equivalent leakage area, or the EQLA. Notice here that that is 147 square inches. That's not quite 10% of a CFM50 of 1400, but it's very close. It's actually more accurate than dividing by 10, but that's where that comes from. Some of you, especially if you are constructing new homes, you might be very familiar with the I codes, the International Energy Conservation Code specifically. The most recent years of that code for southern climates require an ACH50 of 5 or less. For this house, a 1400 is just a little bit looser than that, so it would not qualify. Where I live in Maine, in a northern climate, that value is 3. That's already entered for me. Now notice when I entered that before, and when I click on that as the input, I can see that the corresponding CFM50 for that house is 820. So I would have to make this house significantly tighter to qualify under the International Energy Conservation Code in Maine or other northern climate state. Now, my favorite metric is the leakage at 50 pascals divided by surface area. This is the value that is used by Passive House USA. Now, let me tell you why. If you look at leakage at 50 pascals or CFM50, there is nothing in this metric having to do with the volume of the air in the house or the surface area. In other words, there's nothing that tells you the size of the house. So it's very difficult to compare a bunch of CFM50 values because you have no idea of the size. Now, if we use, on the other hand, the ACH50, we're in better condition because ACH50 requires the volume to be used. So now we have a better idea and we can better compare a large house to a small house, but there's still a problem. As houses become bigger and smaller, the surface to volume ratio changes, and where does the air leakage occur? It occurs in the surface. So ACH50 can give us a slightly erroneous answer. Also, worse yet, it can lead us in the wrong direction. So this one, the leakage at 50 pascals divided by the surface area, as I said, this is what Passive House USA uses, and this is their standard right here, 0.05 for the value, and you can see I entered that there, come up here and see that the CFM50 that corresponds to that is 207 CFM50. You can also see what the ACH50 is that corresponds to that. So I think in the future we're going to see leakage at 50 pascals divided by surface area. Another way of saying that is CFM50 per surface area. That will become a more common metric, and I think it's the best one out there. Let's take a look at the depressurization analysis tool. It's a simple but powerful little tool. Some of you might have seen this chart. This particular tool calculates this chart accurately. The tool solves for building leakage at 50 pascals. We often call this CFM50. This is also sometimes referred to as the depressurization tightness limit, or the DTL. You can solve for exhaust flow
or you can solve for depressurization, and I'll say more about each of these. This is a Solve All tool. You click the radio button for the variable that you would like to solve, fill in the others, and it will solve it for you. The pressure exponent has to do with the leakage characteristics of the house. You just leave that alone or set it if you know the pressure exponent for the house. As with the other red tools, there is pop-up help. You click on any label for an input or a result, and you see the pop-up help. Then to get rid of it, you exit out. For this and upcoming examples, I'm going to use the combustion appliance depressurization limits table, which is available in the Depressurization Analysis Tool user guide. For the example we just went over, I used a -3 depressurization limit. Here's a new example of a practical way to use this tool. We're going to solve for building leakage at 50 pascals, that's CFM 50, or the depressurization tightness limit. So we click on that radio button. For exhaust flow, we want to record what the total exhaust flow, real exhaust flow, is for this house. If I click inside the box, you can see that I've used math on the fly. I have inventoried and measured all of the exhaust appliances in the house. The first 120 CFM, I measured the exhaust flow of a kitchen range hood. I measured the exhaust flow of a bathroom exhaust fan, 50 CFM, another bathroom exhaust fan, and I measured the flow of the dryer, making sure I cleaned the lint trap out first, measured it with a pitot tube, and got 180 CFM. So you can do your inventory right in the input box. We've made it long enough so you can do that. Click outside the box, you get the result. The depressurization, I am assuming, back to the table 1 that I mentioned to you, that I showed you, the appliance depressurization limits. This assumes a water heater installed by itself, not commenvented with any other appliance. It's often referred to as an orphaned water heater. In all cases with depressurization, even though it is in reality a negative number, enter your numbers here as positive. So we can see here that our result for the depressurization tightness limit is 3240 CFM 50. That's quite a loose house. So if we want to ensure that this water heater will not backdraft when all of this exhaust flow is engaged, all of this is operating at the same time, which is a possibility. If the house is tighter than 3240, there might be backdrafting occurring. Now, please understand, this is really important. This is not a surefire way of determining when backdrafting will occur. This is a screening test or an estimation. The only real way to know whether you're going to have backdrafting or not from depressurization is by doing a real-time test with all of these exhaust appliances operating at the same time. For a final example, we are solving for exhaust flow. I've entered the building leakage at 50 pascals, the CFM 50, at a reasonable level of 1200 CFM 50. That's a fairly tight house. Depressurization is entered as 5 or -5. This is the depressurization limit of a natural draft gas furnace. You can see that the exhaust appliances are limited to a total of 269. We would have to eliminate a kitchen range hood or dryer, and it's hard to do that. Let's see what happens if we solve for depressurization. Now we have what I entered here. There are the kitchen range hood, bathroom exhaust fan, and the dryer. I end up with a depressurization in the house when all of these appliances are operating at this tightness level. The depressurization level will be negative 9.22 pascals. Here is the unit here, pascals. This is likely to backdraft a natural draft gas furnace or a natural draft water heater, and I would have to go with a category 3 gas furnace, which has a depressurization limit of negative 15, or a category 4 90 plus gas furnace with a depressurization limit of a negative 25. Let's just see what happens if I put 25 in here. Click outside of the box. You can see it will easily handle the 400 CFM that is being extracted from the house by exhaust appliances. Now let's take a look at the DensPak insulation tool. This solves for both installed density and bag count. Bag count is now selected for the result, and we can also solve for insulation density. I'm going to go back to bag count. We're going to do an example for DensPak cellulose insulation in a wall cavity. Let's now look at the inputs. For the inputs, we have the insulation bag weight. For cellulose, this is generally between 25 and 32 pounds per bag. I've entered 30 here. For framing, we have either hidden framing or exposed framing. My example will be for hidden, but if I did it for exposed, we would be able to see the framing. We could measure it and include it in our measurements. Because we're doing a hidden one, we don't know that, we can't see it, so the tool makes certain assumptions, and I'll show you what those are. We've got gross area. This is the area of the wall that we are DensPaking. Notice that I've entered math on the fly here, so when I click outside the box, I get my result. The fenestration penetrations area, this is windows and doors and other things that are poking through the wall that impact the square footage. I've entered 280 square feet. Here, for the 1816, the 280 square feet is subtracted from the gross area that I entered. Now we're on assembly type. This is for the hidden. We have wall, ceiling, and floor. Notice if I click on the assembly type for the pop-up help, you can see for the ceiling, the framing, which is hidden, is 6.9%. For the wall, it's 25.4%. A significant amount of the wall is framing. So wherever there's framing, of course, we cannot put in DensPak insulation. And for the floor, we have 12%. So those are included as part of the inputs that are under the hood for the tool. So the cavity area, what we have here is the gross area here. Subtracted from that is the fenestration penetration area, and then we have the over 25% of the framing area subtracted also here. So the cavity area, notice that's in square feet, for 1,350 square feet. The cavity depth, I've stated that's 3.5 inches deep for modern 2x4s, and the cavity volume, therefore, is 395 cubic feet, which must be filled with cellulose. Now down to our results. We are solving for bag count. We want an installed density of 3.5 pounds per cubic foot, which is appropriate for cellulose. It would be 3.5 pounds per cubic foot up to 4.5 pounds per cubic foot. The bag count would have to be 46. Now, if you're a contractor, you're going to a job, you're wondering how much cellulose to take, 46 is a good amount. But if we go to the high range for cellulose of 4.5 pounds per cubic foot, we click outside of the box, we see that we have 59. So we could take between 46 and 59 bags with us to this particular job. I'll go back to 3.5 for this, click outside of the box. Well, you might be asking, why would I want to solve for the installed density? What if for the same house a contractor says, or say a subcontractor that you've hired to do this house says, well, yeah, I did that just fine. I've got proper density. In these walls, I put in 40 bags of cellulose. You put 40 here. It's solving for installed density. You see that you get just over 3 pounds per cubic foot, which is an inadequate dense pack. We need at least 3.5 pounds per cubic foot for it to be dense packed cellulose.